In recent times, we have been made more aware of the increasing threat of terrorist acts of violence using concealed explosives to cause damage to property and harm to people. A number of these actions have taken place in buildings or on modes of transportation, such as airplanes and trains. In addition, the number of mail bomb terrorist acts has increased dramatically over the past few years. Mail, in a majority of cases, is transported over long distances by air carrier. It is becoming significantly more important to be able to interrogate baggage and containers at points of departure. Another area of great concern to the public and to our government is the high rate of drug traffic into the U.S. The effects of this problem are well known, and the real issue is how do we impede it? Illegal drugs enter the U.S. by many means, one of which, again, is our airports. Other points of entry include border crossings by people and vehicles, and seaports. For the drug problem, arrivals into the U.S. are of most interest. To counter these problems, numerous devices such as vapor sniffers, dogs, and X-ray machines have been implemented. Although these devices work to some degree, improvement in the detection of both explosives and illegal drugs is needed. This is indicated by the fact that the number of terrorist incidents and drug-related seizures has not decreased. The Advanced Research Projects Agency, among others, is providing the resources to develop improved methods of contraband detection. Under one such effort, the Northrop Grumman Corporation has been selected, along with its project team members, the Tri-University Mason Facility Triumph in Vancouver, and Scientific Innovations on Long Island, to develop a proof of principle contraband detection system, or CDS as it is referred to. The CDS is based upon a nuclear phenomenon called gamma resonance absorption. Gamma resonance absorption is commonly called GRA. It relies upon the fact that certain elements, such as nitrogen or chlorine, will preferentially absorb gammas, or what are sometimes called photons. If a field of photons is caused to pass harmlessly through a volume of substances, and a suitable photon detector is on the opposite side of the volume being interrogated, then these photons can be used to image a volume, and very specifically the presence of key elements such as nitrogen or chlorine. The presence of these elements in certain quantities is an indicator of contraband. The CDS proof of principle shown here is not yet optimized for field installation, but it will serve as a valuable tool to demonstrate the practicality of the GRA detection principle. To generate the necessary photons for interrogation, a particle accelerator is used. Let us examine how the GRA technique works. It all begins with the ion source. Here is where a small amount of hydrogen gas is dissociated into positively and negatively charged particles called a plasma. This process occurs when an electric arc is imposed across the hydrogen gas cloud. By applying a voltage across a series of apertures, we can extract the negatively charged hydrogen ions from the plasma. The negative ions enter the accelerator. Here, an electrical power supply brings the positive charge of the center terminal region up to nearly 1 million volts, which in turn attracts the negative ions. The negative ions are accelerated toward the terminal and then pass through an electron stripper cell. The gas cloud within this cell detaches 2 electrons from the negative hydrogen ions, thereby converting them to positive ions. Since like-charged objects repel, the now positive ions are further accelerated up to an energy approaching 2 million volts at the end of the accelerator. The tandem accelerator employed here has the capability of doubling the ion energy over that of the high-voltage power supply. The enclosure around the acceleration columns serves to contain an electrically insulating gas commonly used in electrical power supplies. The high-energy ions are directed through a high-energy beam transport section that magnetically focuses the ions and bends them downward toward the photon production target. If we look closely at the ions impinging upon the target, we can see a conical fan of interrogating photons being generated. The type of photons produced relies upon the exact energy of the incoming ions and the surface material of the target. At an ion energy of 1.75 MeV on a carbon target, we get photons that can image nitrogen. If the ion energy is changed to 1.89 MeV and a sulfur target is used, we get photons that can image chlorine. Since the target is constantly being bombarded by energetic ions, it is continually rotated and cooled to withstand the thermal heating from the ion beam. A rotating container is used to hold the items to be inspected. As the container rotates, it also very slowly rises so that the incoming photons can pass through every part of the entire volume and at every angle. The resonant photons will pass through most of the contents of the container. However, when explosives or drugs are present, these photons will be preferentially absorbed by the elements of nitrogen or chlorine that are present in this contraband. The detectors monitor the varying intensity of the photons at all positions. The computer data acquisition system stores and processes the data. In this manner, an image of the selected element, either nitrogen or chlorine, can be built up on a slice-by-slice basis, just as is done with present-day CAT scans in the medical field. In addition, there is a continuous background signal of non-resonant photons that pass through the container. These are used to build up a total density image of the container contents, much like present-day X-ray images. The computer compares every voxel of either the nitrogen or chlorine density images to the total density image to determine if contraband is present. An automatic alarm to the operator will be triggered if contraband is detected. At that time, the operator has the option to manually inspect the computer-generated images. If a conveyor system were to be added to the proof of principle device, this approach is expected to be able to process hundreds of bags per hour using a single detection station similar to the one shown here. The entire proof of principle CDS just described is operated through a simple computer console based upon the use of personal computer technology. The mission for the Northrop Grumman team is to develop the proof of principle CDS and verify the practicality of the GRA technique for commercial application by reducing size and cost.